Thank you very much for organizing this webinar and focusing on this important topic. So in my presentation, I will share some of our results coming from the EEG recordings that Brad mentioned at the beginning. So as you have heard, the study included a series of MRI scans, as well as cognitive and sensory testing, and started in the middle of the pandemic. So even though we wanted to measure everything, you can imagine that it would have been quite impossible to use a full, clinical grade EEG system to also collect EEG data on these participants. So we were quite lucky prior to the pandemic to have had experience with portable EEG systems that are very simple to use. And so the system that we used, and we actually brought these EEG electrodes to EEG systems to Sunnybrook, where participants were being scanned in the MRI scanner. And so this system is a dry electrode headband, and it has two sensors on the forehead and two sensors that are touching your skin behind the ear. So I'm going to call them temporal. And they transmit the EEG brain activity wirelessly to a computer that our Ray Hadass was sitting quite at a distance away. And a lot of the participants were actually able to put this EEG headband on themselves. So really allowed us to do social distanced EEG recordings. So participants completed several recordings with the EEG. First was resting state while they sat with their eyes closed for 5 minutes, and then eyes open for 5 to 10 minutes in the beginning. We also collected EEG data while they completed an auditory oddball task and a visual perception task. But for the focus of this talk, I will only be presenting the resting state EEG data. So you've already heard the groups that we had. We had COVID positive participants who self-isolated at home and who hospitalized, but in this presentation, I'm only focusing on the self-isolating group, and they will always be shown in blue in my slides going forward. And then the COVID negative group were the ones who had cold or flu-like symptoms and tested negative on the PCR test for COVID-19. So in the data that I'll be showing, we have 42 participants who came for 42 COVID plus participants who came for their first visit, and then 34 returned for their second visit. And the COVID negative group is, the sample is smaller so far, so it's 14 who came in for the first and 12 returned. As you can see, the mean ages are quite well matched in the two groups, around 40 years old, 41, 42. And there's a larger proportion of females that in the COVID plus group that came compared to the controls. And in the data that I will be showing you, we do look at both visits. So the first visit actually occurred as soon as possible after they were recruited and after they finished quarantine and had 2 negative test results. And so on average, that was around 3.5 months or 4 months after their COVID test that confirmed their status. But as you can see, participants ranged. So because this is an ongoing study and we recruit as many participants as we can, there's interesting variability in the time frames at which they come in. And then once everybody is scanned, we ask them to come back 3 months later for a follow-up assessment. And you can see that the ranges, but overall it's about 7.5, 9 months after for their visit 2. Right, so this is a very brief slide showing you the pre-processing steps. So these are examples of the raw Muse EEG data, and we use bandpass filtering and also ICA rejection to remove the eye blink components. And then subsequently, we extract the power spectrum density, and I will be showing data averaged across the left and the right frontal channels and the left and the right temporal channels. So this is a data slide showing the results that we obtained in the eyes closed condition. And the first row you see the visit 1 data. And as you can see, the blue curve that corresponds to the COVID positive group is overall lower, so showing the reduced power compared to the COVID negative group. And it is happening over a range of frequencies, especially in the temporal channels, and more in the lower frequency range in the frontal channels. And you can also see that that trend is also visible in visit 2 as well. If we break it apart by the frequency bands that people are familiar with, and then you can see the average power across the bands. And overall, the effect sizes that we observed were the most prominent around the theta and alpha bands in the temporal channels in these data. All the pairwise, none of the pairwise comparisons were statistically significant at this stage, but I think it's important to remember that the sample size is small, and this is dry electrode Muse EEG data, so there's quite a bit of variability. Overall, the results look similar in the eyes open condition, where the blue curve again is lower than the red curve, showing reduced power in the COVID plus group compared to COVID negative. But the differences are not really visible in visit 2, except for this higher range in the beta band at visit 2. So these results again break it apart by frequency band, and you can see that there was more variability. And overall, the largest effect sizes, which were around 0.4, quantity of 0.4, were again seen around in the theta and alpha bands, as well as in the beta band in visit 1 and some remaining in visit 2. So how, you are probably wondering, how does this actually relate to symptoms, especially for the second visit? That's many months after their infection point. And we didn't specifically recruit people who would go on to experience long haul symptoms. So one question that I was asking myself is, how does it actually relate to participants who continue to experience long COVID symptoms versus those who don't? So here I'm showing you data on the proportion of participants who at visit 2 endorse the presence of a symptom of these symptoms in a simple checklist. And what you can see here is that our COVID negative group, which is the red graph, are not feeling super great. So they also have experienced symptoms. But the symptoms that you see more prominent in the COVID plus group are brain fog, cognitive complaints, loss of smell and taste, and vertigo. So just as a first pass to look at whether symptoms are related to some of these EEG patterns, what I did was look at visit 2, if there was, if each participant was reporting at least one symptom that is related to the brain, such as loss of smell and taste, brain fog, difficulty concentrating, memory loss, confusion, and so on, the ones that are shown here. And we had 12 participants who endorsed at least one of those symptoms. And we had 18 who didn't endorse any of these symptoms at visit 2. And this is the pattern of their EEG data comparing visit 1 in green and visit 2 in orange. And what you can see is that the people who continue to experience symptoms didn't see a shift in their EEG power between visit 1 and visit 2 in the lower frequencies, and there was still a reduction in the beta band here. Whereas people who don't endorse any more symptoms see an increase in the power in their lower frequencies at visit 2, indicating a recovery. So just to summarize, we overall see evidence of reduced power in EEG in COVID-19 isolated groups over a range of frequencies, but primarily in the lower band, although there is also some results in the beta band. We saw it more prominently in the eyes closed condition. And differences that are still seen at V2 are likely driven by participants who continue experiencing symptoms. And I guess this reduction in power, I think, echoes back to Will's results about the cerebral blood flow that he just showed, looking at reductions in the cortical thalamic loops. I think one interesting takeaway from here, for me at least, for us, is that portable EEG may be a useful tool to be used, a useful tool to enable tracking recovery and monitoring long-term the impact of the virus on brain function. And so again, for the next steps, as Will mentioned, we are very interested in looking at the relationship between symptoms and cognitive function, and brain structure and function, as well as EEG. So we have all these deep measures, and we can look at multivariate comparisons to try to really tease apart, what is the source of this reduction in the EEG power, how it relates to changes in cerebral blood flow, microbleeds, as well as likelihood of experiencing long haul symptoms. And another bigger picture, of course, is coming from someone who is studying the effects of aging on the brain and the risk for neurodegeneration. An important question that we are all asking ourselves is, what are the downstream effects of COVID-19 on the brain, and how does that impact the risk of neurodegeneration? With this, I'd like to thank everybody, most importantly, the participants who have gifted us the gift of their time, their data and energy, and many of them are not feeling amazing, and they're still coming in for these long testing sessions. And I also, among the staff, I wanted to highlight Hadass Grossman, who collected all the EEG data, as well as my undergraduate student Farhan, who helped with processing of the EEG data this summer. And of course, all the collaborators and our funding. And I'm going to end on this slide. If you would like to reach out to us with any questions or comments, contact details are here. Thank you.